Yeah, staple.
No
Staple.
comment.
Not
Yes.
My system is that of something that gets sick really easily. I don't know how I'm not sick.
All right, before we get into this crazy stuff, I would like to talk to you about triangles.
It's the same.
All right, so today we're talking about similar triangles, which are not necessarily congruent triangles. So let's talk about congruency first and what we know about it. So congruent triangles have the same angles and the same size. Everything is the same. For all intents and purposes, the congruent triangles are literally the same triangle, just in a different location, right? It's like someone took a copy of one triangle and pasted it somewhere else. Those triangles are congruent. So all angles, all sides are the same. Now, for both triangles to be the same, that's pretty rare, right? To draw two random triangles and have them be congruent. That's just not likely, right? So there's lots of other cases where we're going to have triangles that aren't congruent, but we still need to get information out of them, and so we need another way to talk about triangles that aren't necessarily congruent, but do have something in common. So let's talk about two triangles right here. Let's play a game of how long it takes you to guess the thing that I actually want you to say. First hour kept it going for a very long time without actually saying what I wanted them to say. So here's two triangles. They're not congruent. I'm telling you that right now. And we know that because, look, these sides are different. So they can't be congruent. So let's make up some sides. How about this, right? 7. So check it out. These two triangles are not the same because their sides are not the same, right? We've got 3, 4, 5, and then 6, 10, 8. So tell me something that you notice about these triangles and try to keep it going for as long as possible without telling me exactly what I want to hear.
Hypotenusely.
What do you see?
The first triangle is half the size of the second.
God. All right, well, this is true. What else you got for me? You guys aren't nearly as fun as first hour.
They're similar.
Yes, they are. They are similar in what way?
They probably have one half.
Because the first one's half the
Third
size.
hour is a bunch of smarties.
6 is actually longer than 10, so that's incorrect.
No? Oh, I mean, it does look that way, doesn't it? It looks to be deceiving. All right, so, yeah, that's true. One triangle is half the size of the other. This one's the smaller one. That one's the bigger one. Also, notice that one triangle is twice as big as the other one. That's also true, right? So one's half as small as one, and one's twice as big as the other. It depends on how you look at it, right? So there's a relationship here. Let's throw some letters down. We have two different triangles, A, B, C, and D, E, F. They are not congruent. They are not congruent, right? But they are similar, as you might say, and they are similar in that they have sides that relate to one another in the same way. So yeah, all numbers relate to each other. Like if I told you 2 and 4, how do they relate? Well, one's double of the other. If I told you 2 and 6, you'd be like, oh, 3 times, right? All numbers relate to each other. That's not a big deal. Being like, oh, look, 2 triangles, a 3 and a 6. That's double, right? I mean, like that happens. If that was a 7, it'd be like, oh, 3 and a 7. How do they relate? Well, one's 7/3 of the other, and one's 3/7 of the other. Okay? It's fine. All numbers relate. That's not amazing. What is amazing is that all numbers here relate in the same way. 3 to 6, 4 to 8, and 5 to 10. Times 2. Or if you look at the other way, divide by 2, right? So the amazing thing here that makes these similar is not that, look, 2 of the numbers have something in common. All numbers have something in common. But that all of the numbers have the same thing in common. So here's what I mean. A, B. Now when I don't put a line over AB, I'm not talking about the figure, I'm not talking about the line segment, I'm talking about its measure, right? So AB is another way of saying 5, right? Are we cool with that? Right? If I put the line over it, I'm talking about the segment itself, right? The segments have certain properties, right? But I'm talking about the measure of AB. Instead of putting a little m for measure like we do for angles, I just write AB with no line over it, okay? AB relates to what side over here? What side does it relate to? EF, right? When we relate things, we write them as fractions to show relationship. AB and EF's relationship is that AB is 5 and that EF is 10. Now that reduces. What's 5 over 10? Half. So the relationship is 1 to 2, meaning that for every 1 over here, you get 2 over there. Does that make sense? Right? I've got 5 ones here, so I've got double the ones over here, right? It's twice as much, right? Or you can look at reverse going half, right? The relationship holds either way. Going from small to big, or from big to small, we have it, right? Going from small to big, we double it. Does that make sense, right? The relationship is 1 to 2. We can write it as a half or 2 over 1, right? Depends on which way you're going. Now, AB relates to EF. What does BC relate to on the other triangle? DE, right? Those are related. And not only are they related, because all sides are related to all sides if you think about it, right? Like we can say 4 is related to 10 because they're both even numbers, right? What we're saying here is that they have the same relationship as AB and EF. So BC over DE, BC is 4, right? And DE is 8. And you'll notice that also reduces to a half. Lastly, let's talk about AC. AC is 3, right? And it relates to DF over here, 6. Which is also a half. So another way to write this is this. I think so far you guys are like, okay, so what, who cares? I see it. Another way to write this is to say this. AB over EF equals BC over DE equals AC over DF. Now, don't be confused. We're not saying that AB and BC are the same thing, because they ain't. AB is 5, BC is 4, right? We're not saying EF and DE are the same, because they ain't. EF is 10 and DE is 8. What we're saying is the relationship between AB and EF, a half, is the same as the relationship for BC and DE, a half, which is the same as the relationship between AC and DF, a half, right? Now, if I flipped one of these, in order to keep it true, I'd have to flip them all, right? Because then it would be 2 over 1, 2 over 1, 2 over 1, right? But it'd still be a true statement. So this right here is the same as this. And given our diagram, what do they all equal? AB over EF equals a half, so all of these equal a half, right? Whereas EF over AB, that flips this, right? Would be equal to that. We cool with that? Right? Again, it depends on what direction you're going. Are we doubling from here to here? Right? Or are we halving? 2 sides of the coin. Are we cool with that? So what I'm saying, and what Chloe was saying earlier, is that these triangles are similar, right? They're not the same, but they have a lot in common. What do they have in common? They have this ratio in common, right? All of the parts relate the same way. AB to EF, BC to DE, AC to DF. They all relate by that. Or if you flip them, they relate by that, right? Okay, depends on which way you look at it. But we call these triangles similar because their parts are proportional. So when I say proportional, what I mean is we're comparing 2 ratios, 2 rates, right? We're comparing AB and EF to BC and DE. So the rate, AB over EF, right, or the ratio, right, the comparison between those two, is the same as the comparison between these two. When we equate, equal sign, 2 comparisons, what we call that is a proportion. What about porpoises? Yes, they relate the same way. Now, we do this all the time. 3/4 is a relationship, 3 over 4, right? That is proportional to what? Give me something that's proportional to 6 over 8, which is proportional to what? Give me another one. 12 over 16, and so on and so forth, right? There are lots of things that are proportional, okay? So when we say these two are proportional, it's just like this, right? It doesn't mean they're necessarily the same, right? AB could be 3, BC could be 6, right? But it does say the relationship is the same, right? At the end of the day, it's all 3/4. So we call this a proportion when we compare 2 relationships. Proportion. It's when there's an equal sign between 2 fractions, essentially. So that's the idea. So when the sides are proportional, all of the sides, not just some of the sides, right? But all of the sides have to be proportional in the same way, right? Then we say that the triangles are similar. So if all of the sides are similar, then we can say that the triangles are similar. This squiggle is the symbol for similar. It's the tilde, right? So you know how congruency, we have the equal sign with the tilde over the top, right? That's congruent. Similar just uses the squiggle, the tilde. Okay? So if we have all three sides being similar, not all three sides the same, right? That's different than congruency, right? They don't have to be the same. They just have to be similar, then the triangles are proportional, right? They're similar. So, pop quiz. Are the triangles similar?
No.
I hear no. Why not?
Because aren't they congruent?
They are congruent. How do you know the triangles are congruent?
They have the same lengths.
Say again?
The same lengths.
They do, right? All the sides are the same. So this is the same as that, right? And we would say that this matches up with this one, right? And then we've got this matching up with that one. So yeah, the triangles are congruent by side, side, side. Our congruency theorem, right? All three sides have matching pairs. Does that mean they're similar?
Well,
Yes. No, they are similar.
Why?
oh yeah, is it like the?
No, because similar means.
I forgot what the example was, but you said that technically because I don't know how to explain
That's
it.
okay.
It was at the start of this whole unit, so
I'm going to tell you they are similar.
yeah.
Give me a reason why they are.
They have the same size.
They do have the same size, but doesn't that mean they're congruent? It does.
Yeah, they go both ways.
Similar does not mean that they have the same size, right? Because these two are similar. So that's not good enough. I need a better reason.
Because they're still proportional.
Why are they proportional? Give it to me.
Because if they're the same, then they're 1/1.
So check it out.
Proportional.
This side, let's call it ABC over here. D, E, F, right? So, AB. What side is AB proportional to? Right? What, in this triangle configuration, what side does AB go with? Yeah. And what's their proportion? Looks like it's going to be 5 for AB. And what's EF? Also 5. What's 5 divided by 5? 1. What does BC go with? DE, right? And their ratio is 4 versus 4, right? Which also is 1. And if you check the last one, AC goes with DF. So, again, for the sides, or for the triangles to be similar, we need to say that all of their sides are proportional. So, is it true to say that AB over EF equals BC over DE equals AC over DF? Is this true?
Yes.
Yeah, right? All of them are 1. So since they all equal 1, yes, they're proportional, or they are similar. These two triangles, triangle ABC, is similar to the other triangle by SSS. Now you can write similarity as SIM after this. I do need to see that. Can't be SSS because that's congruency, right? We've used that before for congruency. You can write SIM, dot is optional, or you can write it as SSS squiggle. Okay? Now, when we say triangles are similar, same as we say for congruency, it's important what order we write our letters in. Okay? So, A, B, C. A is made up of the purple side and the purple side and red side. Purple and red over here is F. So A is going to go with F. B is made up of green and purple, so green and purple is going to go with E. And that means C must go with D because red and green, right? Red and green. So let's go together. Cool. So by SSS similarity, we can say two triangles are similar, right? And again, what we have to look for is not for the triangles to be the same, but for the triangles to be proportional. So 3 to 6 is the same as 4 to 8 is the same as 5 over 10. They're all a half, right? So these two triangles are similar by SSS similarity. Everybody cool with that idea? All right. Turns out even if they're congruent, they're similar. right, so we've noticed already that some of the similarity postulates that we're talking about are similar to our congruency postulates. So let's talk about congruency, and let's talk about similarity. Okay? We know that SSS appears over here as SSS similarity, right? Right? So we have SSS congruency. That's when all the sides are the same, right? We have matching sides that are exactly the same. Here we're saying we have sides that are proportional, right? So they relate to each other like 3 to 6, 4 to 8, and 5 to 10. What other things do we have for congruency? Give me other congruency ones that we had from before. Give me some others.
Side, angle, side.
Side, angle, side. What else we got? Angle, side, angle, right? The inverses of each other. What else? Give me some more.
Angle, angle, angle.
Angle, angle, angle does not appear for congruency.
Yeah,
right?
I meant for the left, right side.
Nope, we don't know that yet.
No.
Angle, angle, side works, and so does side, angle, angle, right? Forward, backwards. What else we got? Come on, what else we got? What ones don't appear over here?
Doesn't ASS still work?
ASS does not work. Remember, ass and ass backwards don't work, but HL does.
Oh, yeah. I thought there was.
Right? That's for hypotenuse leg. Right? Only works for 90-degree triangles. So, this one appears over here for similarity, right? Right? We've just kind of proven that. Side, side, side. If they're congruent, then they're also similar, right? By side, side, side. Even if they're not congruent, but they have proportional, then side, side, side similarity, right? Cool. Let's talk about other ones.
On the left side.
If I have a triangle like this,
Say, you guys simply say.
see if I can do it. It's gonna be a stretch. All right, cool. So we've got this triangle right here. It has certain angles. Now, imagine I made a triangle with the same angles, right? Same configuration. And then I just blew it up a little bit bigger. Would those two triangles be similar?
Yes.
They would, right? When I blow something up, I'm multiplying the sides by the same amount, right? I'm stretching everything by the same amount, so the proportionality remains, right? So what's going to happen is, as I make this bigger, I could end up with a side of 2 over here, and if that becomes 2, what would this become?
It depends on how big.
Well, if that becomes 2,
Oh, wait, what?
this would become, if I'm stretching it evenly,
Oh.
if that becomes 2, that would become 4, and this would become,
I don't know.
There's 3 of them there.
What are you talking about?
So if I stretch this triangle,
Oh, okay.
and I double this side, I get 2, right? So how long would this side be?
4,
4, right? Because it would double, and then this side would be
6.
6, exactly, right? They're all related by that 2 to 1 principle, right? So if the angles are all the same, then the triangles are automatically similar.
Yeah.
Automatically, right?
But-
Now I could stretch it by like 0.2 or like stretch it by 12, right? But whatever I do, it's going to stretch everything evenly, right? And that's going to maintain the angles, and we're going to have similarity. So angle, angle, angle does appear over here, but doesn't appear there. However, do we need to know all 3 angles of a triangle? Do we need to know all 3 angles of a triangle
Oh, wait.
to know that the angles of 2 triangles are the same? So here's what I'm saying. If I've got a triangle here, and a triangle here, and I know that these angles are the same, and these angles are the same, do I know the third angle?
Yes.
Why? Explain.
Maybe
Give me a
backwards.
reason. They're not isosceles, they're not the same angles, right? If I have 2 of the same, then I know.
They all have to add up to 180, so if you subtract that angle from 180
Right.
both times, it's going to be the same thing.
So this angle right here is going to be equal to 180 minus red minus green, right? And this angle right here would also be equal to 180 minus red minus green. By angle addition postulate, these angles would be the same. So if I know 2 of the angles, I get the third for free, right? Almost always, right? If I tell you 2 angles of the triangle are 40 and 40, what's the other angle got to be? 100, right? If I tell you two angles of a triangle are 90 and 90, what's the other angle got to be? 0, right? Which means you don't have a triangle, right?
Yeah.
Exactly. You can't have two right angles in a triangle. But you get the third for free, right? So we don't need to say that we need to know all three angles to know similarity. Really, if we just know two, we get the third for free. So don't bother finding the third, right? So angle does show up. It doesn't show up over here. Which ones would show up over here on both? And give me a reason why. Zayden.
Wouldn't it be all of them?
Why?
Because by corresponding congruent CCP, all of them are going to get side, side, side eventually. So that means that all of them must be over there.
All right, so we are assuming that these triangles are not congruent but are similar. So we can't use CCP. Which ones from over here would show up over there? And why?
Well, if you can prove them congruent, then you can prove them similar.
This is true. But what I'm saying is there's a lot of crossover for stuff that shows up twice, right? Will, if we know two angles are the same but two sides are similar. So if I got something like this. If I've got two triangles that are not congruent, but I know this is 3, and this is 6, and this is 4, and this is 8. And I know these angles match. Where's my purple? Danny, you have a seat.
What are you doing, pen?
I have side angle side. Now notice, I don't have sides congruent, right? I'm not saying that. I'm saying I have sides that are similar. How are they related? By double, right? But I have matching angles. Will these triangles be similar? Is that enough, right, to be something over here? Obviously, it's not the same thing, because then they have to be the same sides, right? But it is enough to get it done in one, right? Same thing with these guys. That's what I'm asking. Zayd.
That would, if you do that, then that's going to lock in place the other side, because if you have those two angles, then it's going to be stretching them out to a certain length, so it's going to have to be the same length of that side.
Okay, check it out. Here's a triangle, okay, with a certain angle. Here's another triangle with proportional sides. Let's make this work. With proportional sides and the same angle. So this angle and this angle are the same. I've squeezed them together as much as I possibly can. The sides are proportional because we've got 2 to 1 and 4 to 2, right? So I have proportional sides, and then I have an angle in between them that's the same. Now, without me having to draw that third side in, I think you can tell how long it has to be, right? There's only one way to make this a triangle, and it's a side length of exactly that, right? So if we know 2 of the sides and 1 of the angle, it locks in the other side for what it has to be. So if these are proportional, then this will be proportional, right? And then by side, side, side similarity, the triangles must be similar. So side, angle, side is enough to get it done. Because it kind of leads to side, side, side in a way, right? So there is such a thing as side, side, side similarity. Now notice, the angles have to be the same. The sides have to be proportional. Does that make sense? Right? The sides aren't necessarily being the same. This says all the angles and all the sides are the same, right? 2 matching angles, and then 2 pairs of sides that are exactly the same. That's congruency, right? For similarity, it says angles are the same, right? They need to be congruent, but the sides only need to be proportional. So 2 to 1, 4 to 2. Does that make sense? So that one does cross over. What other ones would cross over and why? Zayden.
Would ASA cross over because the angles are always going to be the same, and then you have a proportional side that those angles are going to be the same length.
Sort of.
Sides.
Sort of, yes. I need better reasons. What do you think? Why would these guys cross over, or would they not? Come on. Don't be afraid of being wrong.
If you can get like two angles similar, then why wouldn't the side added be like?
Right, exactly. So check it out. That's great. So check it out. We already know that angle. Remember, when we're talking similarity, the angles do have to be exactly the same, right? If we have two congruent angles and that's allowed, well, wouldn't two congruent angles and then a proportional side be just overkill? Yeah. So yeah, there's no angle side similarity because if you're doing that, you've already done too much, right? Angle's enough to get it done. Same thing here, right? We have two angles that are already the same, right? So angle's enough to get it done.
So like the past few weeks we've been doing overkill?
No. For congruency, this is required.
Alright.
For similarity,
Similarity.
it's much less strenuous, right? They're not exactly the same. That's pretty specific, right?
Alright.
Similar is like, right? They're proportional. It works. Notice angles have to be the same, right? Sides have to be proportional. So sides can be different as long as they're proportional, right? But angles have to be exactly the same. What about HL? Would that transfer over or no?
I don't think so.
Why not? What's your intuition?
Wait, so
Think about it for a little while. Would
Well-
HL transfer over?
yes.
Luke says yes. Why?
Because as soon as you have a right angle,
So we have matching right angles, right? Because otherwise we wouldn't be able to use HL, right?
and then if you have a right angle on the side, then you have angle side.
So if we have hypotenuse leg, that means we have one like this, right? We have a hypotenuse and one leg, and we know this has to be 90, right? Another one, like this, right? Should match up. But we don't know this angle, right? So couldn't I like switch this down here a little bit more? What if I made it down here instead? Why wouldn't that work? Think about it, think about it, think about it, think about it. Right? I assumed this angle here, that they're the same. What if it's different? What if I made it like that?
But don't you have the sides anyway, so it has to be.
Right? This one would go down to here, and it would hit 90, so it's going to look really bad. Right? And it looks like, yep, that works. HL's enough to get it done, but I assume that angle. So that angle could be different, right, than this guy. So I made a different angle, and that would make something like this. HL doesn't work, or does it?
Wouldn't it work because you have side and side?
I assume that angle right there, right? I've got ASS, right? Why doesn't HL work, or does it? Notice that I assumed this angle in order to get this to lock up, right? And it looks like, oh yeah, proportional, right? Similar. But what if I don't assume that angle and I assume it's a little bit bigger, right? Then I've got something like this. This side is going out to here now, right? I move that side down to here. Zayden.
Because that means that there wouldn't be a 90-degree angle, therefore one angle wouldn't be the same.
This angle right here just got smaller. It's no longer 90. So if this is 90, there's only one way to get it done, right? This kind of locks everything else in. So HL does kind of appear. But what really is happening here is it's locking in both these angles automatically. So really it's another angle. Or side angle side if you want, kind of like David was saying. So HL does kind of appear, but it's really going to give you more of like this type of thing, right? So really we only have 3 similarity theorems, postulates, right? I can't prove it, but I can demonstrate it, right? These things, side, 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 double angle, and SAS. Double angle takes care of this, it takes care of that, it kind of takes care of HL. Okay? Those are the 3 we're going to use. Here we go. Let's take out that worksheet. triangle similarity worksheet. We're going to be doing this tomorrow as well. Here we go. We're going to prove that these triangles are not the same but similar. Look at them. We have triangle ABC, that's this big triangle. And then we have DEC, which is this top triangle. Right now, it doesn't look like they're congruent unless somehow DE is actually the same thing as AB, right? Maybe I just drew it really poorly and DE is the same line as AB and they're the same triangle, right? But at the very least, they're going to be similar, and I'll show you how. So we know AB and DE are line segments and that they are parallel. So that means this. As soon as I mark parallel, what should you be thinking in your head? What?
Corresponding.
Yeah, we should be looking for cap, right? So we know that. Let's prove the triangles similar. Now we know that to prove them similar, we can use side, side, side similarity. We can use angle, angle similarity, or we can use side, angle, side similarity. Now, spoilers, did they give us any information at all about these sides? No. So there's no way we're going to be able to pull information out of our butts to say what these are, right? Imagine two triangles where the bases are parallel. Do you know anything about their size? No. Right? Nothing. So, like, I could extend that down further and it would still be parallel and it would change the relationship of the sides, right? So we're not going to use those two. We need to get two matching angles. Two pairs of matching angles, I should say. So, what do you think? What should we do?
Maybe we can get the sides together.
Can't get the sides congruent. There's no way it's going to happen. We have no side information. Right? We're going to be using AA. Guaranteed. No, what do you think?
I put by cap angle CDE is equal to, or is congruent to angle CAB.
Exactly. So to help you guys see that, I'm going to extend my parallels, which you should always do. Right? X, Q, L for Landry, and P for pi. All right, so X, D, E, Q. L, A, B, P. So let them be, right? Cool. I'm also going to extend, actually I won't even bother with it. Guys, check it out. Corresponding angles right here and here. You agree? Top right corner of the intersection. If I were to extend this, top right corner of the intersection, right? By CAP, angle CDE is congruent. They are the same angle to CAB.
Doesn't that make the triangles?
Nope. Remember, angles isn't enough to prove them congruent.
But then don't you get the other side? And then converse isosceles?
Nope. That's a good point. That's a good idea, right? If both of those were congruent, right, then we know, oh, look, those two sides are congruent.
Oh, but they're not.
But we'd have a problem, wouldn't we?
Yeah.
You can do
So
Because
you
these
go.
angle CED is congruent to
Okay, by the same logic, this angle and this angle are going to be the same. Now notice, the blue is not the same as the red. It could be, but we don't know that, right? All we know is those two go together and those two go together. Could they both be the same? Sure, right? And then we got isosceles. Great, fantastic. But we don't know that for sure. But we do know that the reds go together. So we got CED congruent to CBA, exactly. All right, so great, we got that. What else do we get? Obviously, we can get vertical angles here and here, but who cares? We're talking about this triangle and this big triangle.
Wait, we can't do by like AA?
Yeah, we're done, aren't we?
Oh.
By angle, angle, don't just write angle, angle, has to be the similarity thing. You can write SIM or the squiggle. By angle, angle similarity postulate, triangle ABC is similar to the other triangle. Now, we got to match up angles here.
So A is good.
A is our first letter. It goes with D on the other triangle. Does everybody see that? A and D go together. B goes with E in this diagram, and then C goes with itself. Guys, turns out we didn't need to do cap twice. Check this out. We could have done this proof a lot faster. Notice that they share this top angle.
Oh, so shared.
Remember how you guys said shared angle? I'm like, no, it's vertical angles. What are you doing, right? This thing, there's no such thing as shared angle. Well, it turns out there is now, sorry. See how this top triangle uses that angle? And this bottom, this big triangle also uses the exact same one, right? Their angles overlap. So we can say by shared angle, right? Angle C is congruent to angle C. Now, so what I'm showing you is that I didn't have to do cap twice. I could have done shared angle to get angle C and angle C congruent, right? And then I could have done cap once, and I would have been good to go, because that's angle, angle. You with me? right?
Yeah.
Go.
So by AA squiggle,
Yep. AA squiggle.
ABC would be
It's
congruent.
my rap name.
What would ABC be congruent?
Not congruent, similar. Remember that's what it means. Similar means that they're not the same, but their parts are proportional.
How would I write that? A squiggle?
Yep, squiggle, just squiggle. No equal sign squiggle, but just
Squiggle
squiggle.
what?
DEC. Right, those two triangles. Top triangle, the little guy,
Oh, okay.
is similar to the big
So we're
triangle.
finding similarity.
Yeah, exactly, right? AA is enough for similarity. It's not enough for congruency, no way, right? That's cool. So, awesome. Look at number 2. We're given that BD and AE are line segments. That's all that means, right? So BD is a line, EA is a line. There's no like weird break like a bendy straw here. Okay, it's all straight through. Is that cool? That's what that means. BD, line segment, AE, line segment. B and E, those angles are congruent. So we can put those together. That's given. We're going to prove the two triangles similar.
What's the BD and AE give us?
So if you look, it just says BD line segment, right?
Yeah, so those
That
are
just means that
all
BD is a straight line. There's no bend after C. Does that make sense?
Yeah.
Right, okay, cool. Right. So what do you see? What do you see? What do you see? What do you see? Zayden. Vertical angles.
No.
By vertical angles theorem. Can't call them angle C's because there's lots of angle C's, right? Angle BCA is congruent to angle, let's do EDC, or ECD, I should say. C has to be the middle because it's the vertex, right?
BCA is congruent
BCA, ECD. Right? Can't just call it angle C because there's lots of angle C's, right?
It's like I did that on the class and it's like.
So, now what?
to.
By angle, right? We're done. By angle similarity, we know that triangle ABC is similar to the other triangle. Again, we got to match up angles. A is the unknown angle. Remember, if I have two angles, I get the third angle for free, right? So that means A and D must be the same angle, right? So A and D are going to go together,
Big brain.
right? B and E are going to go together, and C goes with itself in this case, right? So we're done.
Yes, sir.
The two triangles are similar. Which means if I told you that this side was 3 and this side was 5, well, BA matches up with ED over here, right? And CA matches up with this. So a possible answer could be that 6 and 10 were the lengths over here, right? Does that make sense? It could have also been 12 and 20, right? But they're going to be proportional. That's the beauty of similarity. That's what that can tell you. Congruent means they're exactly the same, not nearly as exciting, right? But it's kind of cool. Let's look at 3. Here we go. Given the measure of angle C is congruent to the measure of angle DEA. So C and DEA, those two angles, are the same measure, right? That's what that little m means. And they're both going to be 90 degrees. So if you look, DEA is this angle here, and C is this angle here. So they're both 90. That's all it's saying. Right? That's all it's saying. We're going to prove AD times BC equals AB times DE. What? Okay. Calm down.
What's the
First
dot mean again?
thing, it means times. Yeah, so the measure of AD, well, however long this is, if you times it by however long BC is, it'll be the same as if you times AB times DE.
I don't know.
So basically, it just means they're congruent proportional.
Yeah, but basically, because proportionality is division, right? So we can move that around and get multiplication good.
So would it give us useful information if we do like by CCC?
No, we can't use CCC. That's for congruency only. We're doing similarity. So
no, what LT?
LPT, no, that's linear pair theorem. Don't worry about that. We can get that other 90. That's true, but we don't need it.
Okay.
All right. So here's what we're gonna do. We're gonna prove the triangle similar first. This triangle here, and then the other triangle. There are only two triangles in this diagram, right? Little guy and big guy.
Yeah.
How can we do it? What do you see? Zayden. Shared angle. See how the big triangle and the little triangle both share angle A?
Yeah.
So, by shared angle, angle A is congruent to angle A. Is that enough to prove the triangle similar?
No. Yes. Yeah.
Why?
Angle, angle.
By angle, we have two angles, right? We have A and a 90, and And we have a and a 90 for this triangle, right? So the triangles have to be similar. So, it's not yet. We know that triangle ABC, that's the big triangle, is similar to the other. Now we got to match up stuff purposely because we're going to use this to prove the next part, okay? A goes with A, right? And then B on the big triangle is this angle here. It must go with D, right? And then C on the big triangle must go with E, right? So here's what we're going to do. You know how we have CCP corresponding congruent parts?
Yes.
We have corresponding similar parts, CSP. So I'm going to say by CSP, I know that the parts are similar. That doesn't mean they're congruent, right? We can't say they're congruent. It means they're similar. So here's the idea. See how AB and AD are in first and second position?
Yes.
That means AB relates to AD in a certain way. And that way that they relate will be the same way that BC and DE relate, which will be the same way that AC, first and third, right, and AE relate. How they relate, I don't know, right? But I know that they all relate the same way. So check it out. AB is the hypotenuse on this guy. It should relate to the hypotenuse of this guy the same way, right? They should be proportional. If this is 6, maybe that's 3, right? Something like that. BC is this. It should relate to DE.
And there's a.
It's kind of weird, right? But it does, right? And then AC is going to relate to AE the same way.
There's also a.
Again, it's based on this. CSP, corresponding similar part. Similarity means proportional, right? So we're going to prove that AD times BC equals AB times DE. So here's what we're going to do. Notice that AD and BC are here and here, and DE and AB are also here and here. So I don't really care about this guy, right? How can I rearrange this equation to make that equation? Luke,
Just.
how can I rearrange this equation to make that equation? Ignore this. How would I do it?
Well, you gotta somehow get AB over DE, right?
Yep, AB and DE need to be on the same side, right?
Right.
How would I do that?
I don't know.
Zayden?
Multiply both sides by AD and then both sides by DE.
So check it out. If I multiply this side by DE, right, that gets rid of division by DE. And now it's over here. So I have AB times DE over AD equals BC. Do you guys see how I multiply by DE to move it over? Is everybody cool with that? And then how do I get AD and BC together? Same dumb crap, right? Multiply both sides by 80. When I do that, I get AD times DE equals BC times 80. Now I can rearrange that to make it look just like the top, right? And then I win. So I'll write AD times BC equals AB times DE. Right, it's all multiplication, right? I'm just rearranging it. I'm making this side on the left, this side on the right.
Okay.
So I'm using reflexive property, right?
What would you do with
And then I'm done.
the things on the bottom?
Things on the bottom.
Like the, what's it called?
all the time.
So here's what I did. I had this, right? So what I did is I multiplied AD to this side and DE to that side, and that's what I got. And then I just rearranged it to make it look just like that.
Oh, yeah.
So it turns out when you multiply those together, they're going to be the same number. Now, note, this doesn't mean that AD and AB are the same thing, right? It doesn't mean that BC and D are the same thing. It could be something like this. It could be 3 times 4 equals 6 times 2. Could be something like that, right? Doesn't mean they're the same. It just means they come out at the same thing when you multiply them. This is going to be useful for proving some stuff that we're going to do next week. And we're going to kind of do that tomorrow with number 4. Buckle up. It's going to get insane, okay? Again, all this means is that they're proportional, right? And their proportionality is 2, right? Double.
Should we try for it?
No.
What if I do?
Do it.
Wait, so
Oh,
you guys-
baby, man.
It's going to take the whole page.
Yeah. The whole page?
It sucks.
Oh, yeah.
Mine's getting a little.
Oh, yeah.
Wait a minute.
Well, you should
Maybe
have.
after
Yeah.
Yes.
Yeah, we're gonna need CSP, and we're gonna need to somehow make it equal to.
Yeah.
Here, we had no idea how they relate, we just know they do. Right? Yeah, exactly. We know they're similar, but not how, right?
Yeah, or how it
And that's because if I move that, right, it changes how they relate.
Yeah.
David's playing 25 minutes.
Yeah, buddy.